Good afternoon and welcome to Live from NOIRLab at Arizona. I am your host for today, Rob Sparks, and we have our moderator, Jamaica Marshall, with us. Our guest today is Hubble Fellow Emma Beasor of NOIRLab in Tucson, who'll be talking about a very exciting subject, one I really love, how massive stars live and die. We got massive stars, we got star lives, and star death, which are just fascinating topics. Remember, if you have any questions or comments, you can enter them in the chat box and we will relay them to Emma for you. First, before we begin, I'd like to take a moment to tell you a little bit about Kitt Peak National Observatory, which is our facility in Arizona. Kitt Peak is funded by the National Science Foundation and is a NOIRLab facility. It was founded in 1958 and is about 55 miles southwest of Tucson on land leased from the Tohono O'odham Nation. We are indebted to them for letting us use one of their sacred mountains for astronomical research. Kitt Peak is home to about over 24 optical telescopes, as well as 2 radio telescopes. We always like to start off our show with a piece of recent news, and NOIRLab's Lars Lindberg Christensen has received the prestigious Klumpke-Roberts Award. You can see right there, that's a very nice picture of him. First, I'd like to tell you about awarded to an individual or individuals who have made outstanding contributions to the public understanding and appreciation of astronomy. The Astronomical Society of the Pacific's Klumpke-Roberts Award for 2021 goes to Lars Lindberg Christensen, Head of Communications, Education, and Engagement at NSF's NOIRLab. The award recognizes Christensen for more than 30 years of bringing science to the public and increasing awareness of the universe and its role in human understanding. Christensen's leadership in the field of astronomy communication to the public began with a keen interest in astronomy and a vision for science communication. By spearheading the communication and education of large science organizations, such as the European Space Agency's Hubble Space Telescope operation, the European Southern Observatory, and the International Astronomical Union, along with his efforts in building global community of astronomy communicators through outreach, technology, and global connections. Christensen has given people the ability to make educated decisions regardless of nationality, age, gender, or socioeconomic status. Christensen will receive the Klumpke-Roberts Award at the Astronomical Society of the Pacific's Virtual Awards Gala on November 19th, 2021. So we definitely offer a hearty congratulations to our fearless leader, Lars Lindberg Christensen, for this award. We will also put the link to this award and our announcement about this award in the show notes. We may add it to the chat here when Jamaica gets on. If not, I will try to get it there, but it will also be in the show notes for this when we actually post the video. And now, without further ado, let's get on to our special guest. Oops, I'll just stop sharing there. Our special guest is Emma Beasor, who received her PhD from Liverpool John Moores University in 2019 under the supervision of Dr. Ben Davies. Currently, she is a NASA Hubble Fellow based at NSF's NOIRLab in Tucson. Her research focuses on the evolution of cool supergiant stars with the aim of constraining the progenitor supernova connection. So I'd like to welcome Emma Beasor to the show right now. Good afternoon, Emma.
Hi, Rob. Thanks for having me.
Oh, yes. Well, I'm very excited to see this because I had you on the 365 Days Astronomy podcast a couple years ago, which is a great episode. I'm looking forward to the expanded version. So this will be a little bit, this have visuals too. So I'm looking forward to the visuals as well.
Yeah, I'm looking forward to it.
Okay, so you may share your screen and take it away.
Okay. Right. Okay, so that should be full screen now.
Yes, I see full screen.
Okay, perfect. So thanks for everyone for coming to watch my talk. As Rob said, I'm going to be talking today about how massive stars live and die, which is my primary research area. So as a basic introduction, I think it's important to remind people what a star actually is. And the best way to do that is to look at our nearest and the most famous star that we know of, which is our sun. So this is a lovely UV image of our sun. And you can see that there's a lot going on the surface of it. There's loads of like flares, there's outflows. It sort of looks really granulated. Whereas if you looked at this star if you looked at the sun with your eyes, it would just look really smooth and yellow. So looking at different wavelengths, you can really see that there is a lot going on with the sun. So the basic structure is as follows. A star and the sun has a core, and this core is extremely hot. And the core is so hot that it can fuse hydrogen atoms into helium atoms, which is what's powering the star. So it's got a lot of hydrogen within there. And with the 10 million Kelvin temperatures that we reach in the core, a lot of energy is produced. Outside of the core, there's a radiative zone, which is just really highly energetic light, and that transports some of the energy from the core to the outer layers. And then we get to the convective zone of the sun, of the star. And this convective zone literally physically moves the energy from the radiative zone to the outer layers. So it's like when you boil a pan of water, like it's physically moving the heat upwards. But today we're not going to be talking about stars like our sun. We're going to be talking about stars which are much bigger. So the stars that I'm going to be talking about have about 8 to 30 or 8 to 40 times much mass as our sun. So they weigh a lot more. They've got a lot more stuff going on. And because they're so much bigger, they live really short, fast lives, and they are much more rare. And you'll see how much faster their lives can be through this talk. So we're going to begin the story of how these stars live and die with how they're formed, and they're formed in star-forming nebula. So this is probably a constellation which is very familiar to a lot of you. So we've got Orion here. So this is Orion's belt. Up on the top left, we have his shoulder, which is a red supergiant star called Betelgeuse. And then down here, we have Orion's sword. And you can see that it looks like there's, a few stars in there, and there's like a smudgy pink thing. And this is the Orion Nebula. So that's what a zoomed in image of this region looks like. And a nebula is basically a region with lots of gas and dust, a lot of hydrogen. And it's where massive stars and all stars are born. So the Orion Nebula is one of our nearest massive star forming regions. You can think of it like a stellar nursery. This cloud of gas and dust doesn't just sit there. It has its own gravitational pull. So at some point, the cloud of gas and dust starts to collapse. And you can see that the structure of like these dust clouds, this is a different one, is kind of lumpy. And what happens is that gravity sort of clings to these sort of knotty structures. So you end up having a cloud that's collapsing, and material builds up around these knots. So as the cloud collapses, you end up increasing the pressure and increasing the temperatures, and eventually from this cloud you will form a protostar. And I will just show you a diagram of what's going on. Let's see if this loads. So you have a cloud of dust, and it starts to form. And in simulations like this, you can see that the sort of areas that are more dense, the more white areas are denser areas. And along these sort of dense regions, you get stars forming. So you can see them forming now, the little white dots. And that's how they begin to form. But they don't form stars as we know them straight away. What they do is they form something called a protostar. So that's this here. So this is an artist impression of a protostar on the left. So you've got all of this material collapsing around these knots. And as the material builds up around these knots, they start to spin, and you get a protostar. So it's not quite a star because at the moment it is not burning hydrogen. There's no hydrogen fusion going on. It's just not hot enough for that yet, but it is spinning, and it's getting more dense. And again, I have another video to show you what's going on. So as all the dust builds up around this high density area, you get your protostar forming. The intense spinning means that you get some magnetic jets coming off. So we can see in the image that there's quite strong jets in the north and the south poles of the object. And this is an artist impression, and that on the right was a simulation of what's going on. But the data looks more like this when you look at it. So it's sort of a little smudge in the middle, which is the protostar, and then you can kind of see where the jets are coming off the object. So I've highlighted them with the arrows there. And because they're forming still in this cloud of dust, it's kind of hard to see them. So they're hidden behind all of this dust there, because of course not all of the dust in these clouds will go towards forming stars. Some of it will form the planets, some of it will form asteroids and stuff, but a lot of it will also just stay as dust sort of floating around, and it really obscures our view. It's really difficult to see what's going on with protostars, but at some point they do heat up enough that you can start to fuse hydrogen into helium. And depending on the mass of the clump or like the would-be star, this process can take a different amount of time. So for a star like our sun, it can take like 50 million years, whereas for a more massive star, it will probably only take a handful of million years to do this, to collapse. But once the stars have collapsed enough and the cores have heated up, they reach around 10 million Kelvin, and then you can start to fuse the hydrogen into helium, and the star has power, so it is counted as a proper star. So at this point, we move to the main sequence of evolution. So this diagram here shows a Hertzsprung-Russell diagram. So very simply, what it is if you looked at stars within a cluster or a galaxy and you separated them out based on their color or their temperature and their brightness, this is the sort of thing that you would see. So stars spend most of their time on the main sequence where they're burning their hydrogen. So that's where they will live most of their lives. So this is the main sequence here, the sort of long snaky bit in the middle. And again, the amount of time that a star spends on the main sequence depends very strongly on the mass of the star. So for example, our sun at the moment is 5 billion years old, and we expect it is only around halfway through its life. So that will last another 5 billion years. So that's really old. Whereas a more massive star, an 8 solar mass star up to around a 30 solar mass star, will probably only be on the main sequence for a few million years. And while that still sounds like a lot, when you compare it to the lifetimes of these lower mass stars, so stars like our sun, it really is just a flash in the pan in galactic and universal terms. So once a star is on the main sequence, the place to look for these like massive stars is within superstar clusters. And the reason for that is it takes a while to see them, because you have to wait for all of the surrounding dust around the star to move out of your way. So once all your stars have started to form, there's winds going on, there's sort of a lot of evacuation of material. So this diagram just shows the area around a clump of protostars or a clump of new main sequence stars expelling a lot of material. So we can only see it once a lot of the gas and the dust has moved out of the way for us. So here's an example of a youngish, massive cluster, so superstar cluster. And you can see it's kind of evacuated an area, so you can see where the dust is kind of separate from the cluster now. And this is the process which gives us those sort of trails of dust plumes. Some of you may have seen images such as of the pillars of creation. And this is how they form. It's from these young clusters expelling a lot of material, so they kind of free themselves of their natal cloud. So this is M83, which I think is the Whirlpool galaxy. So the best place to look for these superstar clusters is in other galaxies. So if we look at M83 and we have a little zoom in here, every one of these sort of big reddish clumps is a newly formed superstar cluster. So these superstar clusters can contain as much mass as 100 times the mass of our sun, or all the way up to around 1,000 times the mass of our sun, all the way up to like 100,000 times the mass of our sun. So they really hold a lot of mass in these sort of pretty small areas. And I mentioned that it's easiest to see these superstar clusters in external galaxies, and the reason for that is that most of these clusters lie in the plane of the galaxy, which is also where we are. So it's really difficult to see what's going on, because when you look through the plane of the galaxy, there's a lot of dust in the way, from a lot of interstellar dust, so dust between star systems in the way. And dust has a really major impact on astronomical observations. So if you have a star that's emitting light and this light passes through a dust cloud, the dust will absorb the light at different wavelengths, usually sort of in the optical kind of bluish wavelengths, and it will re-emit it at different wavelengths, or just scatter it out of your line of sight. So some of the light from the original star can be lost, And this can cause what you're looking at to look more red than it actually is. It's just that there's dust in the way. So to demonstrate this another way, this figure shows the sort of colors we expect from a star, the spectrum of a star. So this is just in the sort of visual wave bands. And you can see it kind of peaks in sort of the yellow. But if you have a load of dust in the way, it will block out light from the bluer end of the wavelength. So things will appear more red. And another way of demonstrating this is if we look at two clusters, which are kind of similar. They're both superstar clusters, both contain a lot of massive stars. So on the left, we have a cluster called NGC 3603, which doesn't have a lot of dust in the way. So that's the one I showed you before. It's clearly blown away a lot of its dust, and it's not in our galaxy. Whereas if we look on the right, we have Westerlin 1, which is a pretty nearby cluster of stars in the Milky Way. And there's so much stuff in the way that the stars all look really reddened, and some of them will be quite a lot fainter than they actually are in real life. And this is something we have to correct for a lot in massive stars astronomy and in astronomy in general. So if the dust is really, really intense, if there's like way more of it than I showed you before, then you might block out most of the light and just not be able to see anything at all. So this is actually what's causing these really dark zones in the Milky Way, these Milky Way dust lanes. They're so thick with dust that the light can't escape or doesn't get to us. It's just enough of it is scattered away from our line of sight that it just looks like this sort of these black lanes within the Milky Way. So the best place to look for these superstar clusters is in external galaxies and not in our own Milky Way. Although there are some, but they are hard to see. Okay, so a star will eventually, after the main sequence, run out of hydrogen in its core. So it's spent, however many million years fusing hydrogen into helium, but at some point it runs out of hydrogen, and this is when the star begins to burn helium instead, and it will move, for the case of these massive stars, to the red supergiant phase. So back to showing the simple structures of these stars. So when the star is burning hydrogen, you have a hydrogen-rich core, like on the left. So that's just a star similar to our sun. And once this hydrogen is depleted, we move onto the helium burning phase. And the helium burning is a much more gives off a lot more energy than from the hydrogen burning. And because there's so much more energy, the star needs to dissipate this to keep it stable, and the star begins to swell up. So this is a red giant star. So this is what will happen to our sun. You can see the scale of it at the bottom. So it will reach kind of 200. It will reach a lot bigger compared to our sun, but you can still see the sun there. But just for comparison, a red supergiant will extend a lot more than this. So this is an image showing the sun to scale against the famous red supergiant VY Canis Majoris. And you can see when you look at the entirety of VY Canis Majoris, you can't even really see the sun. And you have to zoom in quite a bit to see it. It's just a dot. So it's a really kind of unfathomable expansion. It's just very crazily big.
Emma,
yeah.
Following up on that statement about large red supergiants, we do have a question from the chat. So Phil asks, do only massive stars form in superstar clusters?
So you will form stars across all initial masses, but superstar clusters are young enough that they still contain their most massive stars because their lifetimes are so short. They sort of dominate the light when they're really young. But once these massive stars have died, as I will talk about a bit later, we'll be left with these lower mass stars, and the cluster is then called a globular cluster because its population is much lower mass and they are much older clusters. So yes, they are there, but they're just not really doing much compared to the high mass stars at that point. Okay.
Thank you, Emma.
No problem. Okay, so to put this expansion in terms of the solar system, this is to scale. So you've got the sun in the middle, obviously, and then we move out to Jupiter and Saturn on the edge. So we have to zoom out again. And the red supergiant would expand to about the radius of Saturn. So it's really, really massive. It would just completely destroy everything around it. And the reason it's got an angry face is that red supergiants are not like simple, smooth stars. There is a lot going on the surface. So if you zoom in on, if you could zoom in on a red supergiant, this is the kind of surface we would expect to see. So I mentioned before that they have these massive convective layers, and at the surface of the star, they're sort of bubbling, and these massive cells can sort of take up, half the radius of the star. They can really, they really fluctuate, and it changes all the time. So this is sort of on the scale of, I think it's a few years. You can see the scale at the top. So this is a simulation of what the surface of a red supergiant would look like if we could observe that deeply. But it is difficult to observe the surface of red supergiants for a number of reasons. Like a lot of them are really far away, and even the ones that are really close, they're really bright. So it does take a lot of skill to see a red supergiant surface or what's going on. But in addition to this, red supergiants don't look like this at all when you do manage to image them. So I mentioned before VY Canis Majoris, and this is an image of what we see when we look at the star with the Hubble Space Telescope. So VY Canis Majoris has all of this convection going on its surface, but also red supergiants have these really, really major winds that kick up a lot of material. So around this star, you can see huge amounts of dust. We call it like a dusty shell around the star. And this isn't like a smooth loss of mass. It'll move like, tenth of a solar mass of material in one go at some point, and then it'll go quiet for a bit. But it is really like belching up a lot of material. So we end up with this really fragmented structure. Yeah, so the star is kind of literally tearing itself apart at this point.
Hi, Emma. I have a question from the Facebook chat for you here. This is from someone, Carolita has an 8-year-old son, Eddie, and he's been doing some reading apparently because he wants to know how rare quark stars are. Now, I don't know if you're going to get into quark stars or not, but that's definitely fascinating. A quark star, yeah. He'd like to know about quark stars. If you could say anything about them.
I mean, I'm assuming they're really rare because I don't know anything about them, but I'm assuming that's quite an exotic type of star, but they sound really cool.
I don't think one's actually been discovered yet for sure. I'm not 100% positive on that. I think it's theoretical.
Theoretical, right? Okay. I'm the wrong person to ask.
Okay, well, I'll see if we can find something to put in the comments here later for them after the video gets posted online.
Yeah, definitely. Okay, right. So if we go back to the red supergiants, a famous example, which some of you may have heard of because it was in the news a lot last year, is Betelgeuse. So we're back at the Orion constellation. So Betelgeuse is the shoulder, and it's the 10th brightest star in the night sky. So you can have a really good view of it with your naked eye. We have quite a good view of the constellation here in Tucson usually. And Betelgeuse last year was in the news a lot because it suddenly started to go a bit faint. And this was called the Great Dimming. So looking at these images, which are really amazing images of Betelgeuse, this is a really impressive data set. You can see that from January in 2019, the star kind of looks really smooth. But as you move on, so through like December, you can see it kind of looks like there's something in the way. It kind of looks like there's like a dark spot on the star. And as you move along, you can see it looks kind of like it's moving, but the star definitely got a lot fainter from January 2019 to January 2020. And this led a lot of people to speculate that maybe Betelgeuse was about to end its life because the dimming was quite dramatic. So this plot just shows time along the bottom against like brightness along the y-axis. And like red supergiants do kind of change their brightness quite a bit like through their lives. they're sort of variable. But you can see here there was a clear downward trend, like it clearly got a lot fainter. And yeah, this led to people speculating that maybe Betelgeuse was about to die. But the suggestion that has since been put forward in papers is that maybe there was just a cloud of dust in the way of the star. So this is a nice artist impression of what may have been going on. So as I showed you before, if there's dust in the way, it can like absorb the light and refract it away out of your eye line. So you're not going to see all of the light come towards you, and it will cause it to look fainter. And just looking at that by eye, even just looking at this artist impression, it kind of makes sense when you look back at these images. It does look like there is something physically blocking out the light. So the thing that was put forward was that maybe there was like a dusty veil in the way, making it look loads fainter. But interestingly, you can also explain this just by more sort of physical things, such as the cooling in the atmosphere, because it's so turbulent. If it cools a certain way, it will form certain molecules, and this could also cause it to look fainter. But the dust idea is very nice. You get nice images from it anyway. So the red supergiant phase is probably the last phase that a star of this mass will live through before it ends its life. So we now move. Oops, sorry, Rob, did you have a question?
Yes, I actually have two questions. One I missed before from the beginning. Sorry about that. Stephanie was a milestone follower, which I assume that means she's liked a lot of posts on Facebook or something to get that badge on the profile. It says, I've seen several different answers, but what is the official solar mass of a star considered massive? So how massive stars do you have to get to consider the star massive?
How massive does it have to be? So we say it generally at least 8 solar masses would count as a massive star.
Yeah. Okay, so there's a fairly straightforward answer to that one. That's great. And then there's another one from we have a very young audience today, because we have another 8-year-old watching. David Julian said massive stars could become neutron stars, but how massive do they need to be to become a black hole? And that might be something you're going to get to later. If you're getting that later, just say that
is.
Okay.
Yeah, so I am going to get to that later. So that's a great question.
Okay, so thank you for giving us that preview, David Julian. She'll get to that in a few minutes.
Perfect question. Okay, right. So once the star is at the red supergiant phase, it's probably in its last phase before it goes supernova. So you'll see here there's also a phase called explosive outbursts, and that image there is of a star called Eta Ca, which is quite a famous star undergoing a lot of mass loss and a lot of outbursts. They don't necessarily all do that, but they probably get pretty unstable in the time leading up to supernova. So after that, we move swiftly to the supernova phase. So this sort of shows the structure of an evolved massive star once it's near the end. So the very basic picture of what's going on in the red supergiant phase is that your helium fuses to heavier elements, which fuses to carbon, which fuses to neon, which fuses to oxygen, and eventually you end up with this onion-like structure in the core of the star. So everything's fusing to heavier and heavier elements, but still putting out some energy. And this happens until you get to an iron core. And the iron core, if you fused the iron atoms, it would actually absorb energy rather than give out energy. It's called an endothermic reaction. So at this point, the energy, the powerhouse of the star has stopped producing energy. And so there's nothing to support the star against its own gravity, because that's really what the core of the star is doing. So you've got, gravity trying to pull the star down, but you've got the pressure from all of the energy production in the core pushing out against it. So at some point, the energy stops being put out by the core, and gravity is the dominant thing. So at this point, the outer layers of the star will come crashing down onto the core in a really dramatic event called a supernova. So the star will literally just explode. And I will show you a video of that now. So this is an artist impression, but you will get the idea. So the star is no longer supporting itself against its own gravity, and the outer layers of the star will come crashing down. And so everything we've been talking about here has been, lasting a few million years. But this is really a really quick sort of thing. So once you've got to core carbon burning, the star might only have, hours to live. and then the outer layers come crashing down at something like a quarter of the speed of light. So it's really, really quick. And then the shock kind of bounces off the core. And so after this, the outer layers crash down, and then you end up with a shock front traveling through all of the material that made up the star. So this is what it would look like in X-ray. And as this material travels through the outer layers, that takes probably a couple of hours. The light eventually will reach us, and we will see a supernova in the sky. So we've known that people have been observing supernovae go off for literally thousands of years. So this is an example of some ancient art from, I think, Kashmir in India, which is dated something like 4000 BC. And some people have suggested that the image looks like, while there are two suns in the sky, it may actually be that they were observing a supernova that went off at this time. Another star which was observed to explode historically was supernova 1054A. So it was observed by people all around the world, but quite notably by some Chinese astronomers who called it a guest star because it suddenly lit up the night sky. So you can see the image on the right. I show sort of what that supernova may have looked like, and you can see it's brighter or as bright as the moon, and you could see it through the day. So they didn't really know what was going on with it, but it just appeared in the sky. They called it a guest star, and they kept quite good records of it. And if we look back to where that supernova was documented to go off, we can now trace its remnants, so what it's left behind, which is the Crab Nebula on the left, which is also what's behind me. So these leave behind really impressive remnants, and using that we can trace them back and compare to historical records and see, that supernovae have been getting documented for a really, really long time. But one more recent example that went off, 34 years ago or something, is supernova 1987A. And so this is an image of a nearby galaxy. So supernova 1987A went off pretty near to us, what we would consider near, even though it's actually really far away. So we have good imaging of the start of the sky before the supernovae, and then after it went off. So you can see it's really lit up there. So the light from these supernovae really dominates the galaxies that they go off in. So it can, dominate the light and have much more of an output than the rest of the stars combined sometimes. But supernova 1987A was one of the first objects that we had pre-explosion imaging for. So we knew we thought we knew what the star was before it exploded. But we still follow this supernova now because it's left behind a really cool sort of remnant. So if you look here, this is what the supernova looks like today. So if you zoom in there, you can see it's got this really interesting sort of ringed structure. Did you have a question?
Oh, yes, Emma, I was happy to wait for you to finish your statement.
No, go for it.
Oh, thank you. We appreciate it. Okay, so another question from the YouTube audience, and I want to thank everyone in the YouTube chat for your comments and questions. Keep those coming. So Phil asked, what's the difference between supernova and a nova?
Okay, so that's a good question. So a nova is something that kind of recurs, so it doesn't fully explode. So nova tend to happen at lower masses, so they tend to be lower mass stars, I think. And they will get really bright, but then they'll fade, but then they'll get really bright again. So it could be that they are readying themselves for a different kind of supernova. So we don't see massive stars do that. It's a lower mass star thing, but they get brighter, but they're not destroyed. So they will just keep getting brighter and fainter, and you can sort of track their change in luminosity through time. And some people think that maybe they are on their way to exploding.
Fantastic. Thank you so much, Emma. And I just would like to say, I love how stunningly beautiful your visuals are.
Oh, I'm lucky. There's good images here. Yeah, so 1987A left behind this really interesting looking remnant. So we still observe this all the time. We're still trying to find things out about it. And if you look at the remnant in different wavelengths, so not just in the optical, then you get different bits of information. So this is the image of the remnant in different wavelengths. We've got infrared light, which is sort of the red-orange one in the bottom. We've got the visual light in the green, and we've got the X-ray light on the right. So that all traces sort of different things. And when you combine them, you can get these really lovely, colorful images that you often see in press releases and things like that. But generally, the supernova that we see aren't that near to us. So usually they're in other galaxies. So this is an example of a supernova that went off in the Whirlpool galaxy. So it's the galaxy without the supernovae is on the left, and then on the right, you can see the supernovae is highlighted by the yellow circle. And we're really lucky now because the Hubble Space Telescope has been up taking images for like 30 years or so now. So we have a lot of images of like famous galaxies. So we can use this to directly identify which is the star that exploded. And this is something that I'm extremely interested in. So you see the supernova go off, and then you can look back through all of your archival imaging and identify a progenitor star. So the star that you think exploded. So in this case, if you look at figure A, you can see that there's like a sort of reddish blob there, and this was determined to be a red supergiant. And not only that, you can also wait for the supernovae in these galaxies to fade away, and then you can go back to that location and you can determine whether or not that star has actually disappeared. So if it has, as it did in this case, then you're pretty confident saying that this was the star that exploded, and we know so much about it. So you can usually work out how massive it was. And this is like a really, really powerful test of theory, because we're directly seeing which stars are exploding and which ones aren't exploding. And just for some more Betelgeuse stuff. So when people thought that Betelgeuse was going to explode, some astronomers worked out how bright Betelgeuse would appear in the sky because it's quite near to us, and it was determined that it would probably be almost as bright as a full moon if it exploded, so you would be able to see it, which is pretty cool. Yeah, so these supernovae are really important because without them, we wouldn't be able to make loads of the heavy elements. So supernovae make all of these heavy elements that basically make life possible. So there are other ways to make elements on the periodic table, but the massive stars make a lot of things that are really crucial. So they make all of these processed elements, these heavy elements, and this is fed back into the interstellar medium, and eventually it will form a new nebula cloud, and more stars will form from that. So it makes things such as gold. It makes the calcium in our bones. It makes everything that you need to make a dog. It basically makes everything that we need on the earth, everything that makes life possible for us. And this would be a really great place to say that's it. That's where we stop. It's fed back in. There is another potential end to these massive stars that is that's been touched upon by one of the questions I will now tell you about. So there's sort of new evidence that maybe these massive stars don't produce supernovae at all, that some of them just disappear out of the sky. So this is like sort of the first example of someone maybe observing this phenomenon. So we have like lots of telescopes that sort of scan the sky, and in general, what we're looking for is things that get brighter. We're trying to identify the things that explode. But there was one particular study that was looking for things that disappeared, because it's thought that maybe some massive stars just don't end their lives that way. So this progenitor was, I think, 25 times as massive as our sun. And black holes are really, really cool objects. They're really interesting. It's basically a point where the gravity is so strong that even light can't escape it. So this is a simulation of what two black holes might look like, but they're very, very difficult to image, especially ones that come from lower mass stars, because they're really kind of tiny. But they're really interesting objects. So it would be super cool if this was happening. And just on that, there was some really great data last year from the Event Horizon Telescope team. I will point out that they are imaging supermassive black holes, not the kind of black holes that I'm talking about here that would come from massive stars. So this is one at the center of our galaxy. And this is kind of the closest we can get to imaging a black hole. But even this, you're not going to get beyond the point where the light can't escape. So actually, the black hole is still way smaller than it may look from this image, but this is just really cool. And you can see the material being pulled around the black hole. So as I was saying, it would be really awesome if this is what is happening, but we don't really know. We don't really understand fully the physics behind why some stars would explode and some wouldn't. And it's not even entirely clear that this one has actually disappeared. So you remember before I showed you the spectrum of a star and how if there's loads of dust in the way, it's difficult to see. Well, this star has only been observed so far, sort of the shorter wavelengths. So there is a chance that it's had like a massive eruptive episode. So perhaps like VY Canis Majoris, and it's enshrouded itself in dust so thick that its light is just being really blocked out. And our next best hope of imaging this or showing this is with the James Webb Space Telescope, which is due to be launched very soon after a lot of delays, because that will probe sort of this mid-infrared region. So we'll be able to see whether or not there is actually a star hiding behind dust. So we've now completed the circle. We've had a star-forming nebula form a massive main secret star and a red supergiant, and then it explodes and gives all of its material back, and this will just keep going on and on. So I hope you enjoyed my talk.
Thank you, Emma. Do we have any more questions? And please put them in the YouTube or the Facebook chat now so we can relay them to our speaker, because that'd be great. I also like the way you show that the life cycle of stars, it really is a cycle. So I do have one question I'd like to follow up with. I kind of have an idea of the answer, but I'd like to get your take on it. Obviously, you can't keep recycling this stuff infinitely where stars explode, make nebula, and form new stars. So what is the limit to that when you start having not enough star stuff and too much junk that you can't form new stars? Is there any thoughts on that?
So I mean, it takes a long time to get back to the star forming nebula, right? So so you're saying if it's too processed, or like if there's just not enough. Yeah, I mean, eventually I guess like it maybe everything would be so far apart that it wouldn't have a chance to form these clumps and begin the process.
Jamika, do we have anything else from the YouTube chat? Or any questions you'd like to ponder at this point?
Let me check one more time and see if we have any current questions. We don't have any more questions at the moment in the YouTube chat, but yes, I do have a few questions. So Emma, if people want to go outside and look for stars in these different phases of the stellar cycle that you just showed, is that something they can do?
It is difficult to see. It depends what kind of star you're looking for. Like most stars you see will be lower mass stars just because of the numbers. Because these stars are so rare, like only a few percent, the chance of you like being able to see one is much slimmer. But there are some famous examples. I mean, Betelgeuse is really easy to spot. If you can identify Orion, then you just need to look for its shoulder, and it's really obviously red. So it would be hard to tell whether you were looking at a massive star or not, but you can definitely tell when objects are more red than everything around them.
And then also in just going back to Orion, if they wanted to also look at star forming regions, right? We have the Orion Nebula also right there.
Yeah.
We were talking about earlier, where young stars are formed. So in Orion, we can see an older star at the very end of its life with Betelgeuse. We can see molecular cloud stellar nursery where stars are formed. And then we have also the brightest star in Orion. That is, is that a white supergiant?
Oh, it's some sort of bright blue A star, I think it's called. It's really hot. It's a really hot, bright star. But Orion is just a super cool constellation. And I mean, the fact that you can see the nebula with your naked eye, I think is so nice. And like, if you're into astrophotography, you can get some really impressive pictures of that, like from basically anywhere.
That's absolutely beautiful. So this is a great way for people just with their naked eye, as you just said, to be able to at least see two different actual types of stars just by looking at the
Absolutely.
Orion. Oh, that's fantastic, Emma.
Well, I'll just follow up with what Jamika was talking about. During winter star parties, I do a lot of star parties for the public, and I will tell the story of stars by showing the Orion Nebula first, the stellar nursery, then switching to one of the beautiful open clusters in the winter sky to show them a little bit farther in the evolution, then show the red giants, then go to things like the supernova remnant, like the Crab Nebula. So I will actually try and do a series of objects where I take people through the life cycle of stars at a star party, which is always a lot of fun to do.
I like to do that also, Rob. And then I try to end up where Emma talked about earlier, globular clusters. We just kind of touched on globular clusters, but yeah, I like to end with globular clusters so that we can get that full view of the life cycle before we talk about black holes or planetary nebula, which is the ultimate fate, right, of a sun-like star like ours. And yes, we have another comment. Thank you, Phil. Yes, it's Rigel. Rigel is the blue supergiant in Orion. Thank you, Phil. Yes, so we can see a variety of things that you were talking about today, Emma, right, in Orion. Now, where can we find more information on your research if I want to read some of your papers or follow up?
I don't actually have a website, but I've done a few press releases lately. So if you Google me, then I can come up. I've got quite a unique name, so it's not too hard.
Yeah. We do have another question from the Facebook chat here. Seb's asked, is it common that massive or super M, I assume that means supermassive stars, gather planets around as sun-like mass-sized stars do? So do we know planets around these supermassive stars, and is it as common as for stars like our sun?
It's probably not as common, but it's really hard to actually observe that because the supergiants are so bright. Like it's really difficult to see what's going on. So the best option you have to like observe solar systems around other stars is to look at sort of the sort of solar mass type stars with really big like giants around them, like Jupiter, because that's where you get the biggest sort of difference in brightness. So I mean, they technically should. There's no reason to think that you wouldn't be able to, but the lifetime is also pretty short, so you're probably not going to get anything too big around a massive star.
And I imagine the short lifetime just makes it a little more rare and it's harder to find them because there aren't as many to observe.
Yeah, exactly. So you might be able to, but it would be a pretty short-lived and difficult to see thing.
When we are talking about supergiants, are all stars going to go through this giant phase after they are off the main sequence, fusing hydrogen into helium?
So all stars will start to burn helium, but some of them, like our sun, won't get as extended as this. They'll go through what's called a red giant phase. So they still get kind of expanded. So the sun will still sort of expand, but it won't end with a supernova. It will just kind of expand, and then it will just throw off its outer layers, the planetary nebulae, and then there's got a little white dwarf in the middle. It'll just cool down forever. So it's a much less dramatic end. But everything over, 8 to 10 times the mass of our sun should form a red supergiant and die like this.
I was just checking our chat one more time. Let me say thank you to everyone who has been joining us today, live streaming us, your comments, your questions in YouTube and the Facebook live chat. So Emma, just for those of us who are up and coming in this field and those who are interested in getting into this field, how would someone start their study of stellar evolution?
So I always knew that I wanted to do research of some sort, and I was kind of good at maths, so I started doing physics at uni. And I think one thing that's really helpful is to try and get to read articles and to, if you can, see if you can visit an astronomy department or visit an observatory like Kip Peak, and you'll actually speak to people who are doing the research and find out what's actually going on now. So.
Right. And by joining presentations like this one to talk to
Exactly.
those actually doing the research and the work. Yes, thank you so much, Emma. And Rob, will we be adding a link to those press releases that Emma mentioned in the video description?
If Emma can give me those press releases, I think I know one of them, but I'll have to look for the, if there's others that aren't on the NOIRLab site, let me know, because I'll can add those. Yes, definitely can add those.
Yeah.
So
yeah, no problem.
I also want to give a shout out to our young astronomers who joined us today. So I know we had a couple of kids joining us today. So obviously some of those viewers that I see here have more than one person actually watching the stream at a time.
Yes, yes,
Awesome.
that is fantastic to see. And so maybe viewers of all ages, as Emma mentioned, are excited about the upcoming launch of the James Webb Space Telescope. And so, Emma, you mentioned that with James Webb, it's going to be brand new insights. What can you give us one or two hopes from James Webb that you are hoping to see maybe in the first few years of operation?
I'd really like to find out whether that star has actually disappeared. That would be awesome to see whether it has actually gone or if it has just had this really crazy high mass loss phase, which would also be really, really exciting. And apart from that, I'm just excited to be able to see further and, just get more detailed observations of the things that we're already interested in. But yeah.
And when you talk about seeing further, for those who may be unfamiliar with how astronomy allows us to look back in time, could you give us just a brief explanation of what you mean?
Yeah, sure. So with a telescope like James Webb, obviously it's got these huge mirrors and it will have the ability to just point it for a really long time in one direction if you request it. So the longer you point in one direction, the more light you can gather. So you can gather light from further away. And because of the size of the universe, the further away we look, it's kind of like we're looking back in time. So the further away you look, you are literally sort of seeing the past, and you can kind of see how things have changed from when these stars were first forming to now by looking at things that are nearer.
I think the other thing we've learned today is that if you want to do a field where you take lots of pretty pictures, study massive stars.
Oh yeah, that's what drew me in.
And I do have one last question, not to put you on the spot, but as you're talking about clusters, galaxy clusters, star clusters, do you have a favorite? I know it's probably really hard, but do you have a favorite
cluster?
Yes, a favorite cluster.
Yeah, I do actually really like Westerlin 1. Let me get the image of that back up. Where is it?
And that was actually one I hadn't heard of before, so I was really glad that you showed it.
There we go. Yeah, so Westerlin 1 is like a super nearby cluster. This is actually something that I've published work on very recently. And it's a really interesting cluster because it's just got loads of variety within it, which we don't really see very often. So you've got loads of red supergiants, but you also have these things called yellow hypergiants. There's something called a Wolf-Rayet star, which have really, really intense winds. And it's just really unusual to see all of these objects sort of coexisting. And there's only one cluster like Westerlin 1, so there's just a lot going on and a lot to learn about it. So it's a really cool thing.
Oh, wow, that's fantastic. Yes, we definitely will put hopefully the link to that in the video description. And yeah, Rob, may I ask you the same question? You do a lot of research and especially astrophotography and star parties. Do you have a favorite cluster, galaxy cluster or star cluster?
Oh, wow. I mean, there's so many great ones out there. It's hard to say. There's two that sort of stand out for me, though. I actually think I'm going to pick this one as my favorite. I believe it's M46, if I remember correctly. And it's an open cluster in the winter sky. And the reason I love that one so much is it has an embedded planetary nebula inside of it. So you get to get those two objects in the same field of view, which is really kind of neat. So I like that one a lot. So I'm just going to pick that one since it's one that's on top of my head that I'll be showing soon. Since it's a winter object, so I'll be showing it again real soon.
Oh, that's a nice one. Oh, that's a nice one. And I think I'll just share my favorite cluster before we wrap up, Rob. And I, I really am struggling with this because I think this is such an obvious one, but Omega Centauri is just amazing. And I think maybe Emma can speak to this too. I think it's maybe more realized that that's the leftover core of a massive of a galaxy now, and not actually a globular cluster. Is that right, Emma?
I think you're right there. Yeah, I'm not too sure, but yeah, I think so.
Okay, so then if not Omega Centauri, then Ptolemy's cluster. And Ptolemy's cluster, I believe, is M7. Ptolemy's cluster is just along the band of the Milky Way, and it was just a jewel. I love it. And of course, there's just so many amazing objects right there in that area of the sky. But Ptolemy's cluster has always stood out to me, and I usually try to sow it in the summer.
That is a good one too.
Awesome.
Well, I think we're just about the top of the hour here, so we're just about to wrap up. So thank you for joining us, Emma. It was absolutely fantastic hearing your presentation and chatting with you a little bit afterwards. And thanks to all our viewers who asked lots of questions as well. And
yeah, thank you for having me, and thanks for the great questions.
Before we go, Jamika, I believe next month is live from Gemini, correct? Do you have a speaker there you can tell us about?
Yes. So next month, we are pleased to be hosting live from NOIRLab here at Hawaii. And our special guest will be NOIRLab Director Pat McCarthy. So that will be on the 1st of December, a Wednesday. Look for that promotion coming out soon. And we look forward to you joining us right here on the NOIRLab YouTube channel.
Okay, and with that, I think we will be signing off here. So thank you for joining us, everyone. We hope you join us next month for Live from NOIRLab at Gemini. Goodbye, everyone.